Come on in, everyone. We've got about 3 minutes. Only got a couple of you in here, but if you have any questions, go ahead and ask. Let's see. Can any of y'all tell me what day of the week your lab meets on? Can't remember if it's Monday or Wednesday. Monday. I think everybody's in the same one. Anybody not in Monday? Anybody in Wednesday? Okay, well, you guys are lucky. That means your first face-to-face test is going to happen on the 25th. So yeah, I've got a little bit more time, and I think I will be able to put chapter 4 in there by then. So you're probably going to have, well, you already have test 1 and test 2 are open. I think test 1 was due yesterday, and test 2 is due. I now made it the 20th. So you head to the 25th for the first face-to-face test, and that's going to cover 1 through 4 basically. Anybody have any questions while we're waiting? Only got about 1 minute left. Another one. It's like we got about 8 of you. I think there's only, like I said, 9 or 11, somewhere in between there. So that's good enough. And it's right at 5:20. So I'm going to reiterate, it appears to me, and I think the case is that everybody that's in this class has lab on a Monday. If you don't have it on Monday, let me know, but I'm about 99.9% sure that everybody has it on the same day. That should be Monday. And because of that, that means your first face-to-face test will happen on Monday, the 25th. So that gives me ample time. Today we're finishing out chapter 3, and next time we'll start well enough into chapter 4 for you to be tested literally like the next day. But obviously, I want to give you more time than that. So that's what next test will be on, the face-to-face test. And I went ahead and made test 2 due on the 20th. That should give you ample time to do that as well. So if not, I'll think about it. Like I said, if I think the 20th is still too fast for covering chapter 4, then I'll change it. But right now, as it stands, it's shooting for chapter 4, the tests on chapters 3 and 4 being due on the 20th, and then on the 25th will be your first face-to-face test, and technically that covers 1 through 4, even though it's probably mostly 3 and 4. There may be a test 3. Well, actually, that's technically called test 3. There may be a test 4 that's online that I put up before the 25th. It won't be due before the 25th, but it'll be up before the 25th. So just keep an eye on that. Do not trust the homework dates that it says on Canvas, because that sort of copies dates at random, and then it doesn't change them when I change the date. So if you're wondering about your date, check on the due date that's listed in MyLab and Mastering. If you have a problem with that, if you see, for instance, a chapter that's due and we haven't even covered it yet, then that's the time you want to text me and let me know. But you can be assured, if we haven't covered it yet, that due date is going to change. So at least know that. And so far, we've only covered chapters 1, 2, and 3. And today we're finishing chapter 3, and next time it's chapter 4. So has you can also check the video for those. For I said someone, a couple people, nah, easy for me to say. a couple people came in late, and I was just gonna let you know that obviously you can turn the video once it's posted. You can check out the first couple of minutes to see what you missed, but you didn't miss much. All I was telling everybody was that our first face-to-face test will be on the 25th, and our test 2 has now been opened and is due on the 20th. So you have a week from today to do the online test on chapters 3 and 4. Remember, keep your equation sheet, start making an equation sheet starting with chapter 17. Look in the chapter. Every equation that has either in the left side or on the right side of the equation will have a parenthesis, and then the chapter number, and then a dash, and then a number for the equation, and then a closed parenthesis. Every equation that has that is eligible to be on the equation sheet. So just start going in chapter 17, copying all those down, then 18, then 19, then 20, and just keep that the whole semester, because you can use it for all your online tests. It's open book, but it's easier to flip through equation sheets to get equations than it is through the book. So definitely keep that. And then for the face-to-face test, you can bring in, I don't have a limit on the number of pages you can bring in for equation sheets. I just have a limit on what they have to have on them. I'm also going to do some derivations a day that are, if I remember correctly, are not numbered, but I'm going to tell you that you can use them. So pay close attention when we're in class. Let's go ahead and get started. One more chance in case anybody has any questions. Yes, the face-to-face tests you're only allowed an equation sheet. So you can't do any Google searches. You can't do any notes. You can't do any open book or any of that kind of stuff. All right.
I have a question about that.
Go ahead. What's that?
So, can we have a calculator?
Yes, you're allowed a scientific calculator. You can have scratch paper if you want, blank paper. We normally provide that. So whoever your lab instructor probably will have some white paper they can give you, so you don't have to bring any in. But like I said, the only equations you're allowed are the ones that are labeled, except for, as I said, today I'm going to be listing some that you can keep. Any questions? All right, well, let's get started. I'm going to go ahead and share my screen so we can get started on some projectile motion problem. What I'm going to tell you is that the way projectile motion problems work hinges a lot on this one little aspect. So just about every physics textbook has a photo like this, and your physics book does too. I didn't take time to pull it up because I'm just trying to jump into the work. But it'll have basically this picture of a red ball and a yellow ball next to each other. Obviously, the different colors from different books or whatever. But if I remember correctly, your book has a red ball and a yellow ball. And I can't remember which does which, but if I remember correctly, basically what happens is they're taking a photo of those two balls at like every 10th or every 100th of a second or something like that. And initially, the two balls are right beside each other. And then about, a 100th of a second later or 10th of a second later, the red ball has been shot horizontally and the yellow ball has been dropped. And sure enough, at 1/10 of a second later, boom, they're exactly the same height. And then 2 seconds, 2/10 of a second later, they're at the same height again. 3 seconds, same height again. What that shows you, hopefully, is you get it that the vertical motion, which is how rapidly the object falls, is completely independent of the horizontal motion. So, and it actually goes deeper than just that. That's a case where we shot something perfectly horizontal and then we dropped something vertically at the same instant, and they fell at exactly the same rate and time so that they were always the same height. That literally means if you took a gun on planet Earth with no atmosphere, in other words, you're ignoring air resistance, and you held the rifle perfectly level and shot it from a height of about 5 feet. And then at the instant the bullet left the rifle barrel, you dropped a ball or a rock or anything like that, that despite the fact that the rifle is going to fire all this way and land, on the order of hundreds of yards away, that bullet and that rock are going to hit the ground at the same time. Again, ignoring air resistance. Obviously, air resistance is a big factor when you're talking about shells and that sort of thing. But it's even deeper than that, as you'll see in some other problems later. So what I want to start off first is really what's normally considered a slightly more complicated projectile motion problem, specifically a projectile motion problem that has a different launch height than its landing height. So I am going to imagine a scenario in which we fire a projectile at some angle above the horizon from a cliff, and then that is going to land at the base of the cliff some distance downfield. So let me go ahead and draw a diagram. I like to go ahead and do my coordinate systems early. And you should at least think about a coordinate system, even if you don't draw one. But this is what I'm going to do. I am going to imagine a nice little cliff with a little plateau on top. Like this, okay? And then there's going to be a ginormous cliff that drops down like this. And then there's going to be a long distance away at which a projectile can land. And now I'm going to draw a coordinate system. And the coordinate system is going to have a vertical y-axis and a horizontal x-axis. Whoops. Okay, so that's our x-axis. Not really that impressed with it, but it's good enough, I guess. This is our y-axis. And what we're going to imagine is a projectile is fired and then lands some distance r away. And we want to know that. We also want to know t equal question mark. I'm going to call that THT for hang time. And I want to know v final equals question mark. I am going to imagine that this projectile was fired out of this cannon, and in fact was at the origin when it left the barrel. And in fact, this angle right here, theta, is going to be 60.0 degrees. This height right here is going to be 100.0 meters. And this velocity, this initial velocity that the projectile has, is going to be 20.00 meters per second at 60 degrees. I also would like to know what is H max. I'd like to know T at H max. And I'd also like to know V at H max. Okay, so those are the problems I want to solve. Now, this is kind of neat, but it turns out that you can sort of write out the equations completely separately. The equation for the x direction and the equation for the y direction completely separately. And we can use, because as I told you, the gravity doesn't care. It behaves the same way whether the ball was initially shot upward, shot downward, or shot horizontally, or just dropped. So with that in mind, I'm going to just use my kinematic equations. And just for, say, completeness, we could actually put all this in terms of vectors, but I want to keep it simple right now. So I'm just going to work the problem by writing out the kinematic equations. So here is my solution. So the first thing I want to do is I want to figure out how I could know the x position of the bullet at any point in time t. And our kinematic equations, of course, give us that x is equal to x0 plus v bar t. In this case, since I'm ignoring air resistance, which is what we do with projectile motion, okay? Since I'm ignoring air resistance, the average velocity horizontally is in fact a constant. So the velocity is just a constant going to the right. And according to my picture, it's at the origin at t equals 0. So the x0 is 0 and the v bar it's just plain v, only it's the x component of the velocity. So I could put that, for instance, as let me try a different color. I'm going to say this dimension right here. This is my x component of velocity. And of course, rather than make it all junky, I'll put the y component over here as well. So this is v0x, and this is v0y. And I think you can use basic trig to figure out that v0x is just v0 cosine 60.0 degrees, and v0y is v0 sine 60.0 degrees. Okay. So with that in mind, I can now write that the equation x of t for the actual projectile is just going to be equal to v0, which is 20 meters per second. Let me go ahead and write that in. 20.00 meters per second times time. Someone just came in or tried to come in. So times time times the cosine of 60.0 degrees, which of course we can actually figure out what that is, because the cosine of 60 is in fact well, in this case, it actually turns out to be cosine of 60 is root 3. Oh no, it's 1 over the square root of 3. So let's try. Actually, it's not 1 over square root of 3. I'm misremembering that. It's 1/2. So if I did 20 times cosine 60, I should get 10, and that's what's going to happen. So I'm going to say 10.00 meters per second times t. So that's the x position as a function of time for the projectile. Now the y position of the projectile is a function of time. In this case, we can just use our typical y equals 1/2 at squared plus v0t plus y0. So I'm going to use that. And in fact, what we know is 1/2, the a is going to be negative g. So I'm going to say negative 4.90 meters per second every second times t squared plus the initial velocity. Now, in this case, you're going to take 20 and multiply it by the sine of 60. And this one's going to give you 17.32. So this one's going to be 17.32. And I actually had 3 sig figs for the angle. So this is 1 extra sig fig here, just like there's 1 extra sig fig on the 10 as well. So 17.32 meters per second times time. And then you can see that at the projectile is actually at the origin at t equals 0. So y0 is going to be 0. So that gives me the position as a function of time. I could also, of course, figure out what vy is. So for instance, the velocity y is actually equal to the initial y velocity minus 9.80 meters per second t. And that's just using v equals v0 plus at. Okay. And if I try to do the same thing for the x, obviously it doesn't have any acceleration. So v equals v0 is the answer. Shawnee, Amazon's here. All right, so we've got that. That can help us. So can anybody tell me any information they know about how the projectile is behaving when it gets to the point that we called H max?
There's no vertical velocity.
Excellent. Yeah, that's the key thing. That's the key bit of quote unquote physics that we need to understand about projectile motion. is when you throw an object up, it continues to climb until it reaches a zero velocity. And then at that point, it starts to fall back down. And of course, you can just argue logically from that to say that obviously if it still had a positive velocity and a velocity in the upward direction, it would go still higher. Or if it already had a velocity that was downward, then clearly it came from somewhere where it was higher above. So yeah, you have to by default. So we can do that to figure out, for instance, t at h max. So let's do that. I'm going to say t at h max. That's the first part I'm trying to solve for. So the way I'm going to solve for it is I'm going to say 0 is equal to the vertical component of velocity we found was 17.32. So I'm going to say 17.32 meters per second times t at h max. That's the V0 t, or excuse me. Ooh, I don't want to put that yet. That was a boo-boo on my behalf. Sorry about that. Actually be easier to erase it. That's V0. Now I'm going to say, whoa, Nelly. Now I'm going to say minus 9.80 meters per second every second times t at h max. And that gives me t at h max is equal to 17.32 meters per second divided by 9.80 meters per second squared. And I think you can see that that clearly gives us just plain units of meters per second. So I'm going to divide this by 9.8. And that gives me 1.767 seconds. Now that was 3 sig figs divided by 3 sig figs. So that's one extra sig fig there. So that's one answer. Anybody have any questions with that answer?
No.
Yes, Alyssa? No good?
Well, I say I don't have a question.
Okay, no problem. All right, so that's the time that it will take it to reach that highest point. Now, if we wanted to know what that highest point was, we could go ahead and plug that time into the y of t equation, and that would give it to us. But that's using a value that we already calculated. So it might be smarter to use instead a different equation. So let's do this. Let's do solving for h max. So solving for h max, I'm going to use vy squared. Notice I'll just put a subscript on it, but I'm taking a regular kinematic equation. Vy squared is v equal to v0 y squared minus 2 times 9.80. Actually, I should probably write this with symbols first. So let me do that. I will say minus 2g times h max minus 0. That's really what we're getting at. So when I solve for that, I see that h max is equal to, notice the 2gh is negative. If I pull that to the left-hand side, that's going to be positive, and the vy squared is 0 because we're actually going to set the y equal to 0. The velocity in the y direction finally is 0 at h max. And this one, of course, is just the 17.32 meters per second. So when I go to calculate this, I'm going to get 17.32 meters per second. That quantity is going to be squared, and I'm dividing this by 2 times 9.80 meters per second squared, like that. Notice how I'm just saying meters per second squared when I'm dealing with these units, because I don't need to think so much about what it means. I'm just trying to make sure the units work out right. And if you divide something like meters per second that's squared, that which is ends up being meters squared per second squared, and you divide that by meters per second squared, you're just going to get meters, which is exactly what we expect. Of course, 1.732 squared really is 30. So that's going to be 30 divided by 9.8. So I square that. And that gives, or excuse me, I said 30, it should be 300. That gives me essentially 300 to, 4 decimal places. So that's pretty big. Now I'm going to divide that by parentheses 2 times 9.8, just like it's shown here. And that gives me 15.306. And the units meters, obviously I had 3 sig figs over 3 sig figs. So this 0 and 6 are actually not significant. So that's the H max, and I really should call this H max with maybe a prime on it. So I'm going to do that now. I'm going to say H max prime, because really what I just calculated is the height above y equals 0. So in other words, what I calculated was just this itty bitty part. So now I've got to say H max is equal to 100 meters plus that. So I'm going to say 115.306 meters. So that's the actual right answer. And just for concreteness, I'm going to get rid of this line. See if I can do even better. Yeah, narrowly fit it in here. Okay. And I'll also reiterate that T at H max was equal to 1.767 seconds. So that's another answer we were supposed to get. So I'll block that off here too, just because I didn't get a chance to write it because I was on the edge there. I didn't get to write it with the actual symbol that represented it. Now, here's the cool part. The velocity at H max is really trivial. And let me show you how I'm going to do that. The velocity at H max is just going to be in the horizontal direction. That's the key thing to realize, because as we said, as one of your students said, in fact, the vertical component of velocity is 0 at the top. So really all we're going to have is the horizontal component of velocity, which we found was 10.0. So this is going to be, whoa, I used a different color. This is going to be 10.00 meters per second I hat. And that's the velocity at the top. Any questions on that? All right, so now we can check, for instance, I did tell you that if I plugged in this amount of time into the Y, I should get the same results. So that's a worthwhile thing to do. I highly recommend you do it. I'm not going to do it because we're running a little short on time, but literally consider taking this equation right here and plugging in that time right here. And you should find that you'll get 15.306. And then, of course, you have to add 100 meters to it, because that's just the height above the Y, above the origin. So that's where the extra 100 came in. All right, now we're going to start to look for the stuff over there at the far right side. So let's start off with T hang time. Oops. So T hang time is what I'm trying to get now. And what this means is at what time will the Y coordinate be -100? That's really what we're shooting for. So I'm going to write that in. I'm going to use that Y of T that I found right under the line solution that I've got a star by. I'm going to write -100.0 meters is equal to -4.90 meters per second every second times T squared plus 17.32 meters per second times t, and then plus the initial y height, which, as we said before, was 0. So you look at this and you immediately see, oh crap, I've got t, a t squared, and a constant term. So this is a quadratic equation. I'm going to pull the t squared term and the t term to the left-hand side so that the coefficient of the t squared, will be positive. So when I do that, I'm going to have 4.90. I'm going to write that unit in a way that's most convenient. So I'm going to say meters per second squared times t squared plus minus, because now when it comes over to the other side, it's going to be minus. So minus 17.32 meters per second times t minus 100.0 meters equals 0. So yes, this is a quadratic equation, and the form of a quadratic equation is a times x squared plus b times x plus c. That means I'm expecting pluses, which means I've got to include those negatives, and I'm just going to use the quadratic formula. So the quadratic formula says that t, hang time, which is what we're trying to solve for, is equal to the negative of b, and b is already negative, so that's going to be 17.32 meters per second plus or minus the square root of b squared. I already told you guys that that's going to be 300, so I'm going to say 300 to 3 sig figs, and that's meters squared per second squared, because we're squaring meters per second. And actually that doesn't look so good there. So let me fix that a little better. Okay. So that's 300 minus 4 times a. Well, a is 4.90. So that's going to be 4.90 meters per second squared times c, which is negative 100.0 meters. So you can see the units there turn out to be meters squared per second squared under the square root. And then I'm just going to take 2 and multiply it by a. And of course, 2 multiplied by 4.90 is 9.80 meters per second squared. So you see, when you take the square root of meter squared per second squared, you're going to get meters per second, which is perfect because that can be added or subtracted from 17.32 meters per second to get meters per second. And then you're going to divide it by meters per second squared. So that gives you a unit of time, which is exactly what we expect to get. Okay. Now, we sort of need to follow the sig figs. Obviously, when we squared to 17.32, we ended up getting 300. So 17.32 squared gave us 300, which was only supposed to have 3 sig figs. So I called it 300.0 with a bar under it. That means it's significant all the way to the ones place. Now, when I take 4 times 4.9 times 100, then that gives me 1,960, but that's only supposed to be 3 sig figs too. So that actually turns out to be only significant out to the tens place. So I'm getting 17.32 meters per second plus or minus the square root of 300.0. I'm going to keep the units completely out here and I'll put them afterwards, but 300 plus 1960.0, and the units in here I said were meters squared per second squared. And then all of this is going to be divided by 9.80 meters per second squared. I know that's really hard to see there, but I will help you by showing you right now. It's 17.32 with an underbar under the 2 meters per second, plus or minus 300. That digit's not significant. Plus or minus the square root of 300 plus 1,960, and these 2 digits are not significant, divided by 9.80. So now I've got a little bit of breathing room so I can actually write this, and I'm going to take the 300 and add to it the 1960, knowing that I only have the tens place as being significant, the tens, the hundreds, and the thousands. So that gives me 2,260 that I'm going to take the square root of. So that is 3 sig figs. So I'm helped out by that. So 2260 square root gives me 47.53. So I get I get 17.32 meters per second, plus or minus 47.54. I'm going to call this 39 meters per second. All that divided by 9.80 meters per second squared. Now, you see, if I actually subtract 47.539 from 17.32, I'm going to get negative, which seems like it's unphysical, but I'll tell you, it's not really unphysical. If you imagine launching this projectile from the height of the bottom of the cliff, then that negative time would be how much in the past you would have to fire the projectile so that it reached the 100-meter mark right at the origin, moving at 20 meters per second at 60 degrees above the horizon. So that number, that negative time, does mean something. It's just not helpful to us. So I want you to keep that in mind. That's sort of what happens when you solve the y equation for time. It actually has a complete parabola that it's planning on being done for the projectile. So now that we have that, we can discern that we just need to use the plus sign. So I'm going to say t hang time continued. So I now have t hang time is equal to 17.32 meters per second plus 47.539. And I did 39 just because if I wrote 4 there, it's sort of not telling the whole story enough for me. And I normally keep more than 1 sig fig extra anyways. So that just makes me feel a little bit better. Anyways, this is going to be divided by 9.80 meters per second squared. So when you do this, I'm going to say 47.53 plus 17.32. And now I'm going to divide that by 9.8. I got 64.86, by the way, when I added the two. So it's 64.86 divided by 9.8. And that gives me 6.619. 6.619. Make sure I did everything right. Seconds. The reason why that bothers me is, okay, yeah, I only have 1.7 seconds, so good. For some reason, I was thinking I had 17 seconds is what I got for H max, but no, this should be well under half the time. By symmetry, if I shot from the same height that it landed at, then the mid time should be exactly half the time of the hang time. So in this case, we've shortened that, so it should be a little bit less than half, and obviously half of 6.6 seconds is 3.3. So we're well under half of that. So that's the actual hang time. That's what, if you're a professional punter and you want to be in the NFL, that's the number that you're going to impress them with. So I'm now going to say that T hang time is equal to 6.619 seconds. And I'm going to put a box around it. So we've got that answer. Now I still need to figure out R, and to do R, I could basically just realize that looking at this, the X as a position, as a function of time is just given by 10 times T. So I know it's going to reach the ground at 6.619 seconds. So if I just multiply that by 10 meters per second, that'll give me the X coordinate at that time, which is R. So that's what I'm going to do. Oops. Trying to use the correct color. So solving for R, I'm using X of T is equal to, we already said that. I don't have to write that part. It's going to be equal to 10.00 meters per second times time. So that says R is equal to 10.00 meters per second times 6.619 seconds. So obviously you can tell that's going to be 66.19 meters, and that's the range. And now I'm using that word range. That's normally what we reserve for a projectile fired from a height and then landing at that same height later. And then the total distance that it can go is called the range. But I'm using it here anyways. Okay. Anybody have any questions on that? Now, you might not be able to realize this. Well, actually, you can at all here. So I'm just going to go on. I'll talk about symmetry with this a little later when we do a more traditional problem where it's launched from and landing at the same height. But the main thing is you should know that the horizontal component of velocity for the entire motion here, since we're ignoring air resistance, is always going to be 10 meters per second. So for me to get the final velocity, I just need to find out what the final velocity is at 6.619 meters per seconds. So I'm going to use this now. I'm going to say V final sub Y. Actually, let me do this a little more clean. Let's just say V final is what we're trying to solve here. And what I know is V final sub X is equal to 10.00 meters per second. And what I know far as the Y one is that V final Y is equal to V0Y minus 9.80 meters per second every second times T. So I can say V final Y is going to be equal to 17.32 meters per second minus 9.80 meters per second. I'm going to write it squared this time so it's easier to see what the units are going to become. And I'm multiplying it by 6.619 seconds. Okay. So if I do this, I say 6.619 times negative 9.8. That gives me negative 64.86. And I'm adding to that 17.32. I get, of course, negative 47.53. Actually, let's call that 54. Meters per second. So what that means is our velocity looks like this just before it hits the ground. So here's our x-axis, here's our y-axis, not necessarily the same coordinate that we drew or the same origin that we drew earlier. The main part is the directions that we're thinking about. So what I have here is a horizontal component of velocity that points in the positive x direction and is in fact 10. So I'm going to say right about there is 10.0 meters per second. And then about nearly 5 times as long is this, which is going to be negative 47.54 meters per second downward. And in fact, the final velocity is going to be this vector, v final, and that has a direction I'm going to call phi. So v final, I can immediately write as v final is equal to 10.0 meters per second I hat minus 47.5 meters per second j hat. That's actually the correct answer and it's fine, but you should also be able to know how to put it in magnitude and direction format. So I'm going to take the Pythagorean theorem and use it. So the square root of 10.00 meters per second squared plus 47.54 meters per second squared gives me, now 10 squared obviously has 3 sig figs, and when you square it, it becomes 100. So that's up to the ones place. And then the 47.54, when you square that, that also has 3 sig figs, but it turns out to be 2260, 2260.0516, but that only has 3 sig figs. So that's only good up to the tens place. So I end up getting basically 2000, the square root of 2360.05, but because the 100 was only good to the ones place and the 47.54 when it was squared was only good to the tens place, that means the 0, and the 5 are all not significant. So when I take the square root of that, I get 48.58 meters per second, which is really close to the y component of velocity because it's like 5 times bigger. But that's with 1 extra sig fig. So I can now write this as 48.6 meters per second. And now I'm going to say at, to get this, I'm going to make you guys notice that the phi is, or that the tangent of phi is equal to opposite over adjacent. Notice I'm ignoring the signs. I'm just going to put 47.54. And actually, I don't even have to put the units because you know they're going to cancel out, divided by 10.00 meters per second as well. So you get phi is equal to the inverse tangent of basically 4.754. So inverse tangent 4.754, close parentheses, that gives me 78.12 degrees. That's 1 extra sig fig than we had. So I'm going to say this is actually 48.6 at negative 78.1 degree. And that's actually correct as well. Notice that is our standard position. If you measure it counterclockwise from the positive x-axis, it's a positive angle, and that's considered standard position. So I don't have to do any descriptors. But also, if you measure it clockwise from the positive x-axis, as long as you call the angle negative, then that's in standard position as well. So that's how we did that. And I just put those arrows in there so you can see that. So we've managed to actually solve all the parts of the problem. Does anybody have any questions on how all that was done? No. Oh, the 17.32, someone asked about that. What I did was I took 20 times the sine of 60 degrees, and the sine of 60 is basically the square root of 3 over 2. The square root of 3 is 1.73205 if you want a couple more digits. So 1.70325 times 10, because the 2 in the bottom made the 20 into 10, it gives you 17.3205. So that's where that came from. All right. Okay, all the other questions looks like I answered. So I'm going to do another problem. This is a typical demonstration that I do. I used to do a lot of these. I haven't done it in a while, but we used to go to middle schools, elementary schools, museums, high schools, stuff like that, and do physics demonstrations. And one of them we did was what I called Shoot Barney. And of course, after the Columbine incident, we stopped saying Shoot Barney and we just started saying, you know, play catch with Barney. But I found out that I'm going to use a bullet or a projectile. So if I use a subscript B, then that prohibits me from using a subscript B to refer to Barney as well. So I'm either going to use P for the projectile and B for Barney, or I'm going to use B for the bullet and M for a monkey. Because another problem that's often solved is just like this. What we used to do is we would take and set up a launcher that's just like the projectile motion launcher we use for our labs now. And it has like 3 positions. You can pull it back 1 click and it shoots it out slowly. 2 clicks is a little faster, and 3 clicks is really fast. And it shoots this ball out, this plastic ball out. And we mounted a laser sight or a laser pointer on top of it. So the laser points exactly where you're aiming. And that was kind of cool. But also we put a little photo gate right in front of the barrel. So the instant that the ball broke out of the barrel, it would block the light sensor. That light sensor would tell an electromagnet to drop Barney, because we had a magnet on top of his head and then we had electromagnet above it. Or actually we just had a piece of metal on his head and electromagnet above it. So when the power went off to the electromagnet, Barney would be dropped. So we knew that Barney was essentially dropped at the same instant that we fired. And the big question is, if that's going to happen, like if you're trying to, for instance, vaccinate a monkey in a tree by shooting them with a hypodermic needle dart gun, then you know for a fact, as soon as you fire it, the noise is going to startle him and he's going to drop from the tree. So do you shoot above the monkey, or do you shoot below the monkey, or do you aim directly at the monkey? So that's a typical problem. And we can solve it like this. And I'm going to use completely nothing but symbols, and we'll get a definitive answer. So like I often do, I'm going to start with a coordinate system. So in this case, I'm going to start with a coordinate system in which the y-axis points up and the x-axis points to the right. So there's my x-axis, there's my y-axis, and I am going to imagine that the barrel of the gun is right there, so that the ball is initially at the origin. And in fact, what is going to happen is the ball will do some kind of motion like this. And what I'm going to do is I'm going to come over here and say at some distance D is where Barney, or the monkey, is hanging. So I'll say this is the monkey. And I'll say the monkey actually has a height h, and it's over a distance d. I am going to try to solve for the angle theta. I'm going to say the muzzle velocity we can pretend we know, but I'm going to say the angle theta is what we don't know. So assume we know h, d, and v0, but in actuality, we don't even need v0. Okay. Now, I'm going to do the same thing I did before. I'm going to establish a kinematic equation for the x position of the bullet and a kinematic equation for the y position of the bullet and a kinematic equation for the y position of the monkey. So using my kinematic equations, I'm going to, for starters, because this is a projectile, I know the horizontal one is going to have an initial horizontal position of 0, and it's going to move at a constant velocity. So I'm going to use the equation x is equal to, actually, let's go ahead and make it as a solution first. So I'm going to work out this in blue. So what I know is that there's a kinematic equation that says x is equal to x0 plus v bar t. That's actually the definition of average velocity. But in our case, in the x direction, the v bar is the average of a constant number. So since v is a constant, we don't have to calculate an average. So with that, I'm going to say x of the bullet as a function of time is just going to be, again, using my ability to compute x and y components of a vector. This one's going to be v0 cosine theta, and this one's going to be v0 sine theta. So over here, I'm going to have the initial position 0 because it started at the origin. So x0 is 0, but I'm now going to have v0 actually, I'm going to write the t between the v0 and the cosine theta, so it doesn't look like we're planning on taking the cosine of theta times t. So I'm going to say this is just v0t cosine theta. So that's something that's pretty useful, so I'll underline it. Now I want the y position of the bullet as a function of time. Now I know there's an equation for that. In fact, x is equal to 1/2 at squared plus v0t plus x0 is the equation I'm going to use. In this case, the acceleration is downward and g, and the velocity initially is upward. So I'm going to write v0t sine theta minus 1/2 gt squared. Does everybody see that that is in fact the height of the bullet at any point in time t later? Of course, we're ignoring, once it actually either hits Barney and becomes deflected, or the bunkie or whatever, or if it were to completely miss Barney and hit the ground, we're not paying attention to those times either, but it should satisfy us in all of the intervening periods. Does that make sense to everyone? Anybody have any questions on it? Okay. Well, now I'm going to make an equation for the height of Barney, or excuse me, of the monkey. So I'm going to say y for the monkey of t. Again, this is accelerating downward, but it has an initial position that's h, but it has no initial velocity. So the v0t part is going to be 0. So I'm going to say this is given by h minus 1/2 gt squared. So that's something else that's helpful. Now, this isn't necessarily the way that you would have came up with the solution for it, but it's okay. This is just a really clean thinking way of doing it. If you can't come up with that, the main thing is you try to come up with some of the ideas that I come up with so that you can solve it. So for instance, my big idea here is, now that I have y as a function of time for both the monkey and the bullet, I know in order for the monkey and the bullet to collide, I need those y's to be equal at some point in time. And if I could figure out what that time is, that would be helpful. Well, if I look at the diagram, I realize that the bullet is going to be right above or right below or right on the monkey when the X position is D. So here's my plan. Solve X bullet of T equal to D for time. And I'll call that time T sub D. Then use T sub D for the time with Y monkey of time equal to Y bullet of time. So that's my big plan. Does that make sense to everybody? Does that seem like that should do it? Anybody have any questions on it? All right, so let's start off the first part. XB of TD is equal to D. That tells me D is equal to V0T cosine theta. So T sub D, and actually I should have put a D there as well. T sub D is actually going to be equal to D over V0 cosine theta. And this is super helpful. So I will mark it so that I know where to find it next. Now I am going to put Ym equal to YB. So Ym, the height of the monkey at TD, is equal to YB, the height of the bullet at TD. So this is going to give me, in fact, H minus 1/2 G. I'm not plugging in the time here, but I'm doing so on purpose so you can see something. I'll plug in the time the next time. Right now, I'll just put it as TD. Now that's the Y monkey. Now I need the Y of the bullet. And that, of course, is V0 T sub D sine theta minus 1/2 G T sub D squared. And that's why I actually chose to not plug in the time yet, because I wanted you to see that the negative 1/2 GT squared on the two sides are just going to cancel each other out. No matter what the time was, as long as the times were equal, those two things were going to cancel out. And this is what I was warning you about earlier, is gravity behaves exactly the same whether the object was shot upward, shot downward, dropped, thrown downward, anything, doesn't matter. And you see it right there because those terms drop out. So now I'm going to take the same equation and plug in the T that's left. I'm going to plug in the TD that I know. So here we go. We're going to get H is equal to, notice there's nothing else on the left-hand side now, but H is equal to V0. Now TD is D over V0 cosine theta, and then I have times sine theta, but the minus 1/2 GTD squared is gone as well. So now you can see, oh, wow, the V0s cancel out, and I get, actually, and because of that, I get H is equal to D times the sine of theta over cosine theta, which is actually D times the tangent theta. So from that, I can reach the conclusion that theta is equal to the inverse tangent of H over D, and now we have our answer. Are we supposed to aim the bullet directly at Barney or the monkey? Are we supposed to aim it above the monkey? Or are we supposed to aim it below the monkey? Can anybody tell me based on that answer? Anyone? Okay. Well, notice if we look at this triangle, we could actually make a triangle with theta being the angle. Let me do this with a different color. I'm going to do it with, I don't know, this ugly pink color. Okay. And if I make that triangle, I think you can see that the opposite side has a height h and the adjacent side has a length d. So the tangent would be h over d only if you aim it directly at the monkey. So that's the answer. Any questions on that? All right. So we've only got right at 18, or excuse me, yeah, right at 18 minutes left. I've got one more projectile motion problem I'm going to solve for you guys. And then next week we'll go into chapter 4. You can start looking at chapter 4 and you can start looking at my YouTube channel for applications of Newton's second law or Newton's laws of motion, because the more you know about that, the better it'll be for you, the sooner you have it. So anyways, what I'm going to do right now is I am going to, again, start with a coordinate system. And that's just, again, that's my preference. You don't have to do that, but I like doing it. So I'm going to start with a coordinate system. And this coordinate system is going to have a vertical axis that's called y and a horizontal axis that's called x. And here's my x-axis, here's my y-axis. I'm again going to imagine a cannon or something like that firing the actual projectile so that the projectile will launch and arch over and land right here. So let me change this just a little bit. Let me change this just a little bit. So there's my x-axis now. And again, you see this quantity right here is going to be called R. I want to calculate that. I want to calculate T hang time. And I want to calculate V final. I would also like to calculate H max. I'm going to say T at max so I can write a little bit less than I did before. So I'm going to say that one's a question mark. And I'm going to assume we know that this angle, so I'll put my initial velocity. I'm going to say this initial velocity is V0 and the angle is an angle theta. And we are assuming we know V0 and theta. Okay. So here's the solution. I'm going to do the same thing I did before because that actually is a really wonderful technique. But not only that, I can begin to show you vectors and how they can be handled and worked with and stuff like that. So it sort of plays double dividends. But again, I could just make up the equations for the position in the x coordinate and then for the position in the y coordinate. And what we normally do in physics is we define a vector, specifically a vector that points from the origin of the coordinate system to the location of the object at any time t. And we either call that r of t, or sometimes we'll call it x of t. I've noticed that freshman, sophomore level physics students sometimes get a little bit bothered when you say x of t because they can't separate that x from x, y, z. So I've chosen to use r of t. Now, if I actually write that vector out, then what I'm going to have is I'll say r of t is equal to, now we saw this started at the origin, so both x0 and y0 are both 0. So the x coordinate or the x component of this vector is going to be just the initial velocity times time. So we know that's going to be v0 cos, oops, let me write the same order that I had, v0t times cosine theta, and all of that will be multiplied by I hat. And then we can also say, well, the y component is going to be just like it was before. We've got a initial velocity upward, and then we've got a minus 1/2 gt squared. We've got no initial position. So I'm going to say this is v0 t sine theta minus 1/2 g t squared, and all of that will be equal to, or will be multiplied by j hat. Okay, so that is a way you could work these problems. I don't necessarily recommend it unless you find it comforting and helpful. The main reason I wanted to show it to you is because I wanted you to understand how to take derivatives of vectors, and I wanted you to see that we do in fact get our typical kinematic equations when doing so. So for instance, this is R, the position vector as a function of time. And from what we learned in chapter 2, we can find the velocity vector as a function of time by taking the derivative of the position vector as a function of time. So let's just try that out. So v of t is equal to dr over dt. And dr over dt, if I take the derivative of v0t cosine theta with respect to t, basically v0 and cosine theta are just numbers, and it's multiplied by t. So I take the derivative of a number times t, and I get just the number. Now, you might think, well, what about that I hat? And that's the beauty of I hat, j hat, and k hat. They are truly constant vectors. So they're just a constant. So you don't have to do anything to the derivative. You just keep it there as if it were like a 3 or a 6 times t. So when I take the derivative of this, I'm going to get v0 cosine theta, and the I hat remains. Now, when I take the derivative of the other term, again, the j hat is unaffected. It's just a constant multiplied by all that stuff. But now the v0t sine theta, that derivative just becomes v0 sine theta. And then the derivative of negative 1/2 gt squared becomes negative 2 times 1/2 times gt. So that's actually going to be negative gt, and then the j hat's written there. So you can see the velocity in the x component, it really is a constant. It's just v0 cosine theta. And you can also see that the velocity is the same thing as v0 plus at. Again, that same kinematic equation we had. Now, we know that since we're ignoring air resistance, the only acceleration this projectile should get is really the acceleration it gets from gravity, which should be in the downward y direction. So we should be able to verify that by remembering that A is equal to dv dt, which, by the way, is also d2r over dt squared. But when you take the derivative of v0 cosine theta I hat with respect to t, you get 0. When you take the derivative of v0 sine theta j hat, you get 0. But when you take the derivative of negative gt j hat, you just get negative g j hat, which is exactly what we expected. So all of this looks kosher. That's the main thing. All right. Now I'm going to do the same stuff I did in the Cliff problem, the very first one, to solve for all these values. So let's begin with t at max. T at max, I'm going to take the velocity as a function of time to solve for time, or I'm going to take the v squared equals v0 squared. Obviously, that would be the better one. So I'm going to say, I'm going to say vy squared is equal to v0y squared minus 2g times h max. And that's because the minus, there was supposed to be a parenthesis after the G, and it'd be H max minus Y0, but Y0 is 0 and Vy is 0. So now I'm going to get that now I'm going to get that H max is actually equal to V0y squared. Well, V0y is V0 sine theta. Now I've got to square that. So that's V0 squared sine squared theta. And then I got to divide by 2G. And that's it. Actually, I like this other color. So this is an equation that your book derives, but if I remember correctly, it's not one that they number. So it was supposed to be a equation that you can't use on your equation sheet, but I'm telling you right now, you are allowed to use this one. Okay, so you are allowed to use that one. Make a note somewhere. Okay, I'm not going to be asked to remember them off the top of my head, so you just have to pay attention and get this. Now I've got T max. What I also want to, or now I've got H max. What I also want to do is figure out what, oh, stupid me. I was going to solve for T max and solve for H max instead. So I apologize for that. But anyways, H max is what I was solving for. So we'll just change history and pretend like we did that. Now I'm going to solve for T max or T at max. And the way I'm going to do that is I'm going to set the final velocity in the y direction equal to 0. So I'm going to say V sub y equals V0 sub y minus GT. And of course, that's going to give us, setting this equal to 0, that's going to give us T max or T at max is equal to V0y, which is V0 sine theta, divided by G. Again, this equation, I do not think your book took the time to number, but I'm again allowing you to do that. Can anybody look at the drawing above and maybe take a poke at what you think TH is? Remember T, the hang time? Anybody tell me what it is compared to, for instance, T at max?
2 T max.
Exactly. So you literally just put a 2 in front of that V0 and it's golden. Okay, good job. Now let's try another one. Let's go for TH. So TH is what we just claimed was going to be twice as big. So let's do that. I'm going to say TH. And what happens for TH is the actual Y position is going to be 0. So I'm going to say Y is equal to V0. Actually, I should put a time in there so I don't, so I don't confuse the times inside the sign. So V0t sine theta minus 1/2 GT squared. And I'm going to set this equal to 0, the final position, right? So you might think, oh, crap, we got to do the quadratic formula again. But no, we luck out because in this case, you get 0 is equal to V0t sine theta minus 1/2 GT squared. And remember, the first step in factoring things is look for a greatest common factor. So I can now say that T times V0 sine theta minus 1/2 GT is equal to 0. And that gets me, of course, either T equals 0, which obviously comes from the instant that it was fired. So I'm going to say nope. But the other one is TH is equal to 2V0 sine theta over G, which is exactly what your student, your co-student, your classmate guessed, or actually he knew. Okay. Any questions on that? Now you can actually use that time and use it with the V equals V0 Y GT, or excuse me, with the X equals X0 T, and that'll actually get us a range. So let's do that. You don't have to do it that way, but that's a good way. So now I'm going to say R. So I'm solving for R. And what I'm using is X is equal to, we found that to be V0T, oops, not sine, times cosine theta. So R, which is the X at that time, is equal to V0 times, now I'm going to use that T, that's 2V0 sine theta over G times cosine theta. Well, anybody remember the identity for 2 sine theta cosine theta? That actually happens to be, I haven't seen anybody try to answer it yet. Okay, that happens to be the sine of 2 theta. So now I can say that R is equal to V0 sine 2 theta over G. Notice that's meters per second in the top part and meters per second squared in the bottom part. Something, oh, no, that's supposed to be squared. The V0 times the V0 is there. So that's 2V0, that's V0 squared. So now we get meters per second squared divided by meters per second squared, where the top one was meters squared per second squared. So we just get meters out. That works. And this is actually really relevant because remember, when you're firing a projectile, the only thing that matters is the first 90 degrees. Because if you actually like make it 91 degrees, you might as well just turn the axis around and call that 89 degrees. So really the first 90 is all that matters. But when you've got the argument of the sine being 2 theta, things get a little different. So let me show you what that looks like here. So let's say this is theta, and let's say this is y equals the sine of 2 theta. So we know that the trig function sine theta looks like this, where that's 2 pi. But since the theta, or the argument of the sine, is 2 theta, it's only going to make it up to pi to be there. So now that's going to be pi. That's going to be pi over 2, which is, of course, 180. Excuse me, pi is 2 pi is 360, pi is 180. Half of pi is 90 degrees. And in fact, this one right here is pi over 4, and that's 45 degrees. And what I want you to notice about this is, unless you're trying to get this peak, and unless you're trying to maximize the sine of 2 theta to be exactly 1, then every other distance that you're trying to do has 2 trajectories. It has the one that Shaquille O'Neal uses for his free throws, and he hits about 52%, which is horrible for an NBA player. And then you got LeBron, Kobe, and Michael Jordan. They always hit the other one. And in fact, what that looks like is basically, if you did a position versus time, what you'd see is you can have this projectile, this trajectory, or this trajectory. And this, like I said, is MJ, or Kobe Bryant, or LeBron James. Whereas this one right here might be Shaquille O'Neal. Shaquille. Sorry, that's from the middle. Now, if you happen to be shooting for a maximum though, there's only one angle for that, and that's for sine 2 theta equals 1. So that's what we've learned from this. I think from symmetry, you can now guess what the final velocity would be. Can anybody tell me what the final y component of velocity would be for this?
The initial y velocity.
Exactly. The only difference will be it'll be pointing downward, so it'll be negative. So this is going to be V0 cosine theta I hat minus V0 sine theta j hat, which is also V0 at negative theta. So all of those are completely kosher ways of writing the final velocity as a vector. That's it. So all these 4 or 5 equations that I just boxed off are, as best I know, not numbered, but you're certainly allowed to put them on your equation sheet. Okay. We're done. You guys can go ahead and split. I'll wait for the last person to leave and then I will leave. But thanks for coming, everybody, and have a good evening and a good weekend, and keep an eye on your emails. Make sure you knock out your tests. If anybody missed test 1, you might want to let me know. Hopefully you didn't, because I've given you plenty of warning, but I did find out 3 people missed it in my face-to-face class, so I might have to deal with that. Crack some skulls. Anybody have any questions?
Well, now that you say that, I accidentally took the practice test thinking it was the test.
Mm-hmm.
And I was wondering if I could take the test.
Yes. So here's how I'm going to do it. The actual test, I'm not going to reopen the practice test. That's the disadvantage that people would have for missing the first one. And, obviously it's not fair for those who did finish it on time. So what I'm going to do is I'm going to set the due date to the night at 11:59 p.m. So you now have till tonight at 11:59 p.m. Is that going to be good enough, or do I need to do to tomorrow? Because you have
Well, I
something
can do it tonight.
You can? Okay.
Thank you.
No problem. Good luck, buddy. And anybody else can have it as well. So I just changed the date to September 13th, 11:59 p.m. for test 1. Anybody else? Darnisha, Alyssa?
For the practice test, does that like count for a big part of our grade? Because I did miss that one as well. I thought
Okay.
for some reason that they were going to be due tonight and midnight.
No, so the practice tests are extra credit, but the way they work is I take the highest score of each of the practice tests and I take the average of that. But if you missed one, that means that average is going to be a 0, so it brings your grade down. But I average them, divide that by 20, and that many points is added to your course grade. So you definitely do not want to miss them in general.
Okay, thank you.
It is extra credit. It's not taking away from you. It's just not giving you as much credit. You're welcome, Melissa. Is it Gabriel or is this I think this is Gabrielle, right? Might not be here. All right. Well, good luck, everybody. I'm going to stop sharing the screen. Notice you do have a test 2 that's open. Knock that out. Thanks again for coming. Good night.